Okay, this is lecture 9 in 2018. At lecture 9, we just switched to Schrödinger Poisson equation solver. So that is the second topic of our lecture, and we will follow this way. However, in this year, I feel that we need to think about two-dimensional structures first. So therefore, the content which was covered in, yes, then maybe lecture 13 in 2 years ago is now moved to lecture 9. So today, lecture 9, and the day after tomorrow, lecture 10, we'll talk about the implementation of two-dimensional equations. Okay, so as we did in the one-dimensional structure, we will first do the calculation for Laplace equation first. Of course, since we have already done it in the one-dimensional structure, we'll fastly move forward the final goal. And lecture 10 will talk about again Poisson equation, and you will be able to evaluate the equilibrium structure of our two-dimensional devices, so real device. So this is no longer toy problem. We will learn the realistic analogy. Okay, so anyway, today lecture 9 is devoted to the basic background for solving the Laplace equation in two-dimensional structure. Once you can do it in two-dimensional structure, then extension to the 3D structure is straightforward. Of course, in this course, I will not talk about the 3D expansion, but if you are interested, it's up to you. You can follow the three-dimensional extension. So let's go to lecture 9, and this is Laplace equation. I think that we don't have to spend much time on Laplace equation, the introduction of Laplace equation. Since we have two-dimensional structure now, instead of derivation with respect to x, now we have another one with respect to y. So in xy plane, now our Laplace equation is like a Laplacian operator of our solution function phi should vanish. Yes, we know it. But in my opinion, in 2D, the most tricky thing we have to consider is boundary conditions. So in the previous case, for 1D case, we were relatively free of this issue. You know that here and there we had contact. So this was gate and this was also gate. These 2 points are our boundary nodes, and at that time we just impose certain number to this node and another certain number to that node. That's all. So once we fix the potential, then usually this type of boundary condition is called Dirichlet boundary condition, and we can impose Dirichlet boundary condition without much difficulties. So please remember our previous work. We just impose our Laplace equation or Poisson equation in bulk nodes, non-boundary nodes. After that, for boundary nodes, we just set the value of our solution function phi. That was all. But in the case of two-dimensional structure, so think becomes a little bit more complicated. I mean that, why don't you just draw the target structure in this lecture? So eventually I wanted to think about this type of structure. This is a rectangle, and here we have a certain context or terminal. Let me just introduce different colors to emphasize the context. For example, in this case, we have contact, and another contact, and also another contact. We can think about this case. So we are free to set the value of this contact and that contact, another contact, and also another contact. We are freely setting the value of those terminal voltages. Okay, so yes, although that is different. For example, this is 0 volt, 1 volt, 2 volt, 3 volt. Any numbers can be imposed into these terminals. Yes, that's okay. But point is, this is not the only thing we have to care about. This is not the only boundary nodes. For example, here we have the boundary nodes, however, which are not connected to the terminal. So here and there we have a certain terminals. So we can think about three different cases of our nodes. One is, I wanted to say, bulk node. This is non-boundary nodes. And we can think about boundary nodes. And they can be also categorized into two groups, 1, 2, and 1 is terminal or contact boundary, and this is non-contact boundary. So we can think about three different nodes, and for each of them we can define different equations or different conditions. For example, in this case, we can just apply Laplace equation itself. It's okay. And for terminal nodes, yes, we can apply phi equal to certain number, and this is directly boundary condition. Then the remaining question is, how about the non-contact boundary node? In this case, usually we impose homogeneous Neumann boundary condition. So what is the homogeneous Neumann boundary condition? The Neumann condition just says that the normal component of the gradient of our solution vector is specified something. This is Neumann boundary condition. And when we say that homogeneous Neumann boundary condition, then we explicitly have number 0 for this normal component of gradient of phi. Okay, so this condition, homogeneous Neumann boundary condition, is frequently applied to our non-contact boundaries, not only for Laplace equation, Poisson equation, but later you will learn different equations. But even for these cases, you introduce usually this homogeneous Neumann boundary condition. The reason why you have this type of homogeneous Neumann boundary condition for non-contact boundary is usually we think in this way. We believe that uh, anything interesting occurs in the center of our simulation domain. So at the center of a simulation domain, there happens something interesting and worth to be simulated. Okay, that's the reason why we are introducing computer and some approach to write down computer code to solve this problem. But point is, this is a hot place. Oh, something really interesting happens. But if we go to the boundary of this simulation domain, then what will happen? In this case, something interesting is happening only at the center and we are getting bored. So when we eventually approach it at the end of a simulation domain, then everything should be just uniform and no interesting thing happens in this part. Of course, you can say in this way, or you can ask me this way. Hey, if I set a certain simulation boundary or simulation domain, and even at the domain boundary, something interesting happens, what should we do? The assumption is invalid. Then what should we do? If you ask me in this way, my simple question is, then your domain is too narrow. So when you set your simulation domain, you have to keep in mind that you have to expand your simulation domain sufficiently to cover all of interested things. So if your events occurring at this point, at least you have to set your domain in this way. This is preferred way to set the domain. Oh, the bad way is a bad way is just to set in this way. Oh, what will happen? In this case, you can reduce the simulation domain. Certainly, that will be quite helpful to reduce your computational burden. But that is not all the story. So if you introduce your simulation domain too much, so if your domain is too tight, then your assumed boundary condition is no longer valid for this simulated system. The quality of your numerical solution will be degraded. So therefore, you have to set the sufficiently wide simulation domain for your correct numerical solution. Let me give you a more relevant example. Think about this one, this structure. We have here gate, and here we have oxide. And usually in our course, we are considering the system usually called as a double gate structure. So we have here gate. This is the double gate structure. But think about a more conventional one. So here we have a very thick silicon. So silicon is directly terminated with a contact called substrate contact. Yeah, this is quite common in the MOSFET. So in this case, this is still one-dimensional structure, and you wanted to solve your nonlinear Poisson equation. Okay, so then what you wanted to do is Hmm. Um, since this is quite thick, so this is quite thick, like yeah, that is really order of micrometer order, and you know that this is just angstrom or nanometer scale. So previously you just introduced 5 nanometer thick silicon body. You were quite happy with it. Next time I ask you to simulate this bulk structure instead of double gate structure, then you have find that, oh, this is just 1 micrometer, for example. Oh, you think that when it was 5 nanometer, you just introduce 0.1 nanometer spacing for your silicon body. Therefore, more or less you have introduced just 50 points. So you are quite happy with this number. But if you just keep this number uh, 0.1 nanometer and try to discretize this 1 micrometer long substrate, you immediately find that you need 10,000 nodes for this silicon body. So in order to discretize this silicon body of 1 micrometer thick with zero point 0.1 nanometer spacing, you need more or less 10,000 node points. You don't like it. Oh, you feel that this is too much. So instead of that, okay, why don't you just reduce our simulation domain? So maybe that is not that important for our simulation domain. So your choice, let's assume that your choice is still, you say 5 nanometer, and just to place your substrate contact here. Then your computational burden becomes exactly identical with your previous one for double gate. You have just 5 nanometer thick silicon body by your assumption, or by your mesh setting, or by your domain setup. However, I wanted to ask you whether this solution is really valid for your problem. What is your opinion? 5 nanometer thick uh, silicon substrate, although that is originally 1 micrometer, but in order to just improve your simulation speed, you just reduce the silicon body. Then what is your opinion? I mean that this guy have tried two different things. One is the system itself has 1 micrometer thick substrate that is given, and he or she just introduce 5 nanometer thick silicon whose doping density is identical with the original 1 nanometer thick silicon, and the student solved it and says something, got certain result, and report it. So do you think that this reported value can be valid for this 1 micrometer thick silicon? That is my question. What is your opinion about this approach 1? So approach 1, just to introduce small domain to improve numerical efficiency. It really depends on the situation. Say, I see that this is quite interesting. Let's say in this silicon with 1 micrometer thick body, you have, let's assume that you have 100 nanometer of depletion layer. Assume in this case. Now, from the surface or interface of your silicon and silicon dioxide interface, 100 nanometer depletion layer is existing. So inside it, we have strong electric field. Of course, beyond this depletion region, now we can say electric field is more or less zero. So if we just say only 5 nanometer is simulated in our calculation, then you say that here in reality we have strong electric field at 5 nanometer at that point. But what is the boundary condition superimposed to this artificial contact? So substrate which is moved to 5 nanometer position. Then in this case you will just say phi equal to the phi at your local equilibrium condition. So certainly the value imposed in this way is quite much different with the realistic solution. So the answer is setting the simulation domain to only 5 nanometer thick is not justified from the calculation. Then what is the safe way to set the boundaries? If we have 100 nanometer depletion layer, at least we have to expand our simulation domain up to 100 nanometer. Of course, this is too tight, and we have to have a certain margin. For example, 200 or 300 will be safe choices for our boundary. Okay, so if we say, for example, 300 nanometer, then we still have 200 nanometer between the end of the depletion layer and our substrate. So we have a sufficiently long simulation domain where the electric field is sufficiently diminished and no electric field exists. I mean that if we have a certain reason where electric field is still not vanishing, then we have to include that part into our simulation domain. If we just cut the domain and at the boundary, if we have a strong electric field, that will introduce quite much errors in our solution. It is very difficult to predict the exact position, maximally efficient position for our simulation. So we have a trade-off. If you have a sufficiently wide simulation domain, then you don't worry about the validity of your simulation domain. Everything will be just in your simulation domain. However, that introduces much computational burden in your calculation. So usually you want to reduce it as much as possible, but if you just exceed a certain range, the quality of your solution will be degraded. Practically, since you have certain knowledge about the depletion layer, then usually you understand that where is the sufficiently safe range. So now we expand our discussion to two-dimensional case. In this case, now we have a silicon and silicon dioxide on top of it, also silicon dioxide in bottom. So here we have silicon dioxide and silicon dioxide. And as I told you before, here we have contact and contact and gate contact and bottom gate contact. Okay, we have already discussed about it. And then my question is, then how about the length here? How about the length here? What is the required value for this source and drain region? So the best way from the viewpoint of numerical quality of our solution is just to set a really long structure and just place your contact at the end of this long structure. Then you will find that every electric field will diminish in this highly doped region. So you know that in this part actually doping density is order of 10 to the 20 per cubic centimeter. So you will find that you are quite safe in terms of numerical accuracy or physical validity. But you know that this is too long. Then you have to spend quite much computational burden for your, once again, unnecessarily many nodes. So this is also very curious question. So I wanted to introduce a really extreme case. Oh, since in this MOSFET, every important thing just occurs in the beneath of a gate. Somebody thought that. So why don't you just simulate in this way? Here we have oxide, and here we have oxide, and here we have silicon. And since I wanted to introduce the maximum efficiency, so let me just introduce my source and drain contact in this way. Here I have source, here I have gate. This is source and this is drain, and this is a gate and this is gate. If I simulate in this way, then what will happen? What happens to my simulation result? If I draw my IV characteristics based upon this short source and short, almost no source, no drain region, then what will happen? Of course, the result will be quite off from the realistic one, because by introducing certain equilibrium conditions at this point, we just disturb our correct physical description. So we have introduced very unrealistic boundary conditions into those points that will ruin your solution. So your solution will have a very bad performance or bad physical description about the solution. So the thing is, now you have to think about what is the position of our source contact and drain contact. Then we have no predefined way, but anyhow the position of your source contact should be placed not to disturb the behavior at the source side end of your channel. Whether you have a contact here or whether you have a contact slightly further, there should be no differences in your channel behavior. Otherwise, your choice of boundary condition will affect your solution itself. That is not a recommended way to simulate the MOSFET. Not only the MOSFET, every simulation should be considered in this way. You have certain region where interesting, here interesting means that high electric field and strong current density occurs in certain part, and you have a certain surrounding part. Yes, you have a hot place, and this is your relatively warm place, and your contact or domain boundary should be placed just away from this hot place. That is my main message in this slide. Okay, so we have a long discussion about setting the boundary condition, but I think that is a really important one in practical sense. Okay, so then let me go to the remaining slides. So I think that we have covered an important message about setting the simulation domain. Okay, so then let's go to our example. In this lecture 9, we will consider a rectangle. Here we have 9 points along x direction and 5 points to y direction. So you have just 45 discretized points inside your system, and all of them is just space with a uniform spacing delta. So here we have spacing delta, also spacing delta all over our simulation domain. And as I told you before, we will think about mixed boundary conditions. Here mixed means that we have introduced both of Dirichlet boundary condition and Neumann boundary condition. So we will think about these two one. Before talking about the boundary condition, we have to think about how can we assign certain physical quantities into the solution vector. This is was to discuss. So since now our domain is 2D, so at a first glance, since we have 2D, why don't we introduce just a solution matrix instead of a solution vector? So in this case, for example, x now has, for example, 9.9 by 5, and each entry in this matrix is just corresponding to each point. For example, this point is corresponding to this point is corresponding to this point, and this point is corresponding to that point. So that will be quite easy, but you know that this is not the way of our Newton-Raphson method. Newton-Raphson method anyhow requires a solution vector. So although we have a two-dimensional domain or even three-dimensional domain, that should be mapped into a vector. So in other words, although we have a two-dimensional space, they should be labeled with an integer index. For example, that should be 1, 2, 3, 4, something like this. Or you can say 1, 2, 3, 4, 5, 6. Anyway, is quite acceptable, but anyhow we have to introduce certain way to label them all. So in this course or in this example, I just introduce an indexing method based upon our index IY and IX. So if we have a certain ix, iy points, then we will label it. For example, this is 1, and this is number 9, and this is 10, this is 18, 27, 28, something like this. So therefore, that should be 35. Please note that this index system is not the optimal one. So there is no preference between them. So I just said in this way because this is my preference. So there is no specific way for us, for all of us to follow this indexing system. So please follow your preference. So anyway, in this case, we have labeled them all, and starting from, for example, number 1, we are ends up with 45 and 44. So if I have a certain index ix, iy, then it can be easily converted into this index pair can be easily converted into what? Into a certain index. And this index is used to specify location inside your solution vector. And of course, we should provide the inverse relation. When you have a certain index, for example, 44, then you should be able to find out that is corresponding to 8 and 5. You can easily find the inverse relation. So now we assume that you have this facility. Then think about the discretization and boundary condition. But discretization itself is quite straightforward. You know that, as I already explained in our previous lecture, when we have certain form which is given of divergence of gradient of phi should vanish, and this form is integrated over certain volume. So we have now introduced certain volume integration. Then with the divergence theorem, now we have surface of that volume and gradient of phi and dot product between our infinitesimal area. So now we have this form, and in this two-dimensional case, now we have top, bottom surface, and right surface and left surface. So by using this decomposition into 4 different surfaces, now you can easily get this discretized form. If you are not familiar, or you can get easily this form by your own, then I wanted to recommend you, please watch our lecture 8.5, which is devoted for this lecture 9. So I hope that all of you can easily follow this problem or this result. And now let's go to, okay, this is our example, and once again we have 9 and 5 setting, and here we have 3 contexts, 1, 2, 3 contexts, and this is an analogy of our usual source, and this is a drain, and this is corresponding to our substrate. And in this case, we can, for example, apply 0 volt to source and 0 volt to substrate and 1 volt to our drain contact. This is the situation we will consider in this course. And for other nodes, so with this lines, they are corresponding to non-contact boundaries. In this case, we have introduced the homogeneous Neumann boundary condition. So this is our toy problem. We'll talk about this one. And Dirichlet boundary condition, whether this is 0 or whether this is 1, doesn't matter. You can easily find it. For example, let's follow in this way. This is 9, 5, and you have to introduce phi 9, 5 equal to 1. Then, since your 9, 5 is actually corresponding to number 45 in the vector, so when you build your matrix AX equal to B, it is just contribute to 45th row, and here you have phi sub 45, and you have just number 1 in 45, 45, and number 1 again from this number. Think about this one. Now you have 1, 1. This 1, 1 is corresponding to 1. So your original equation phi 1, 1 should be 0 can be now casted into your first phi should be 0. Then this will contribute the diagonal 1 in 1, 1 component, and you have a phi 1, and it should be 0 because you have 0 here. Okay, so then let's go to the Neumann boundary condition. So I think that this is the most tricky part in this two-dimensional expansion. So when you consider the homogeneous Neumann boundary condition, we have to think about this one. This is just the expanded view of our left boundary. I mean that I just magnify this part, only this part. Okay, then if we are considering the point where, so here, if this is the center node, actually it has the surrounding node 1, 2, 3. For bulk node, if we are talking about this node, then we have 1, 2, 3, 4 surrounding nodes. However, we are now have a missing node here. So that is the point. In this case, let me just simply summarize. When you apply the homogeneous boundary condition, just apply your main equation, your equation applied to your bulk node without modification. That is my rule. So for example, here previously you have just to impose Laplace equation. Then if you are solving Laplace equation, please solve Laplace equation even for this boundary nodes when this is not attached to your contact. Then you will find that this red box is a somewhat different from the previous one. Previously we had a square, however now we have a half of a square, a rectangle, and previously we had 4 surfaces, but now we have 1, 2, 3 surfaces and 1 missing surface. But with the help of homogeneous Neumann boundary condition, actually the flux vanishes. So you don't, in reality, you don't have to worry about this left boundary. You can just neglect it. That is the help of our homogeneous Neumann boundary. So instead of considering 4 boundaries, you can just think about 1, 2, 3 surfaces. Yes. So that's so simple. That is the point. So when you follow it, then you can find this relation. This is already well explained in our lecture 8.5. So if you cannot make it by yourself, please watch the video. Then you can immediately find the way to derive it. Okay, so therefore I think that we have already covered all required content, and you have homework number 9. So still you have 2 days, and you can just solve our toy problem, 9 by 5 problem. So you have 45 unknown variables, just to solve it. And now you have 4 different sub-problems with different boundary conditions. So the first one is drain is 1, all others are 0. And the second one is source is 1 and all others are 0. And third one is substrate, or sometimes called body, that is 0 and all others are 0. And finally, we have source, body, drain, all of them are biased with 1. Okay, so please make a comparison between these solutions, and I think that that's all for our homework number 9. So homework number 9 is particularly simple, but homework number 10 will be more difficult, so get ready with it. So I will just wrap up this lecture. So see you this Wednesday. Bye.